Albert. So next we have Albert Lee from OmniTI. He's going to be talking about sandboxing OpenZFS on Linux.
All right, so let's kind of come up with some air from the in-depth ZFS talk, and let's talk about containers for a while. How many people have used zones on the Lumos of Solaris? Okay, so a good number. So what about the? I guess I'm just going to go into some background that might be kind of old hat for a lot of people, but for a few people, I think it'll be at least somewhat useful. So, okay, so I'm Albert Lee, and I work at OmniTI now. Used to work at Exenta. You may know me from mailing lists such as the Lumos developer list. So, zones were a technology, introduced in Solaris 10, and it's kind of there was similar things like FreeBSD jails before that, and so on. But it's a way to isolate all these resources so you can have multiple workloads on the same system that would otherwise share resources, but in a way that you can actually manage that and the kind of the boundaries that might be exposed in a potentially vulnerable environment. So you anyway, so of course, like that kind of predates like the kind of modern era of lightweight containers, but it certainly has the sort of same principles, and it kind of took inspiration from jails and stuff like Linux vServer, where you had that sort of same single object encapsulating all these resources, named resources, file system, IPC, so on, and presented something that looked like a virtual machine with low overhead in terms of CPU and memory usage, and it was a fairly lightweight abstraction through. But they also took that a little further by basically turning that into something that would be managed through like the normal system. There would be a normal set of system tools that you just spin up a zone as it were a service. And also APIs that would let you your applications work a little better with them. So yeah, again, zones encapsulate all these resources, named resources, and there's a zone object out there, and attached to each process, when interpreting privileges for a process, they're done in the context of the zone. So yeah, so you have root in a zone is actually unprivileged with respect to what we call the global zone, and there's also a lot of resource accounting and stuff that you can do on a per zone basis. And so the initial global zone is basically what the normal Unix environment was kind of designated, and then non-global zones, kind of get they're stateful because they have configuration associated with them and a specific identity that's persistent across reboots and so on, and you can spin them up fairly easily that way. So. And there's also interfaces into the zone infrastructure, which is what we're most interested in right now, that let basically drivers or subsystems in the kernel interact with zones in a meaningful way and provide that same sort of resource isolation. So when ZFS was integrated, there was delegation support added for ZFS. So first of all, zones, of course, you could specify that some list of mount points is associated with a zone, and that becomes under the zone's own file system tree. That those are a separate set of mount points, but You could also delegate ZFS datasets to zones, and this is part of the zone configuration. You could specify lists of datasets that would belong to the zone, and within that zone, you could administer, all of the. You could use the ZFS command as you normally would in the global zone, and it would. The delegation was exclusive to a zone, so one dataset. It was a one-to-one mapping of a dataset to a zone, basically. And zone datasets would be visible from the global zone, but would not be mounted there. And there obviously there's some limitations because of the way the zone integration worked. Because it was part of the zone configuration, you can modify that without restarting the zone. And it's a one-to-one mapping. So in the case of Linux, when the port was done for ZOL, the actual calls into the zone framework were all preserved in the ZFS code, more or less, and the Solaris porting layer, which is the component that talks to that kind of prevents the Solaris kernel interfaces to ZFS code on ZFS on Linux currently. They basically stubbed all those the zone related calls to just tell ZFS that it was always running in the global zone, which makes sense at the time, especially because the Linux as you'll see, the infrastructure in Linux for containers was also kind of in flux. It's much more standardized now. So Linux containers are, they kind of exist. So Linux presents actually a set of primitives, right? Instead of a single object that's a container. So in their equivalent of the proct, the task struct, there's a set of namespaces associated with the process, and this is actually, anyway. So in these namespaces, each one refers to a specific named resource, similar to, if you remember from list and zones, like say mount points. The mount namespace isolates basically the tree of mount points available, and there's stuff like IPC, network, basically all sorts of individual types of named resources that kind of compose the interface that process has to the system. So, and then more recently, user namespaces were added that basically map a set of UID and GIDs to another range. So that's what finally allowed UID 0, for example, in a Linux container to be mapped to something unprivileged. And the other piece of the puzzle for Linux containers was control groups or C groups, which basically was a separate mechanism that let you specify resource limits and also just get resource control information. And then in this, you would construct another parallel process tree for each type of resource, and it didn't actually have to. These trees could be structured however you want them, really, and didn't have to match the actual the real process tree, but in terms of hierarchy. So Linux containers are fiction. They're basically this collection of namespaces, and the associated file system that you dropped on the top level of the mount namespace, and a collection of control groups to actually manage all these resources and limit them. And of course now we have all these this explosion of container platforms that kind of just encapsulate all this stuff and present something that approximates a unified like container interface. So when you spin up a container, you're always you're really under the covers. It's assembling all these primitives into a set that your process runs under. So the problem for ZFS is, of course, that ZFS, when you're running a process inside a container, and you want to make it, you're running the ZFS command, and now the ZFS at the kernel level gets the call from there, and it has no idea that you're actually running inside a container. There's no specific single piece of context that it can refer to say I'm running inside a container and I should behave possibly differently if you want to have sort of the same feature set that you would under zone. So there's no single object that identifies a container uniquely, so to allow like container-specific behavior. So really, the kind of solution that we went with is, well, first by just saying, well, data sets are just another resource named resource, like say network interfaces or mount points. So we ended up introducing another namespace, and the namespace kind of infrastructure in Linux is sort of extensible. You don't directly like grow the task struct or anything, but there's another structure attached to that kind of can change its size without breaking too many things. Okay, so I call it DataSet just to be kind of amenable to maybe in the future this is useful for more than ZFS. Although the way it's structured right now, it's unlikely that ZFS, anything other than ZFS, will really be able to take advantage of it. Although I'm open to potentially fixing that. So the other piece is the zones code is still pretty much all there in ZFS on Linux. So it's just that every time it checks if it's in a zone, it thinks it's in a global zone. So basically, in the Solaris porting layer, those entry points into the zones code have to be actually fleshed out to say, well, maybe I should look at what namespace is attached to my process, and look at the DataSet namespace and see if I can use that to decide what quote unquote zone I'm in. So there's this fake zone object that we kind of interrogate, and then that actually has an associated namespace. So for each namespace, we have a mapping there, and for each DataSet namespace, we have a mapping there, and we kind of just treat that same way as we would treat an actual zone. So there's so in the initial global zone, there's also an initial DataSet namespace, and then all of the other namespaces are non-global zones, at least for the first pass. So there's no namespaces. The other thing about namespaces is they can be nested, so you can have inheritance and interesting containers within containers and stuff like that. But the existing zones code kind of it was flat. So zones, you were either in the global zone or you were in a non-global zone. And so the zone object has a list of delegated data sets, and that's how it worked in the actual zones implementation. And doing a similar implementation here lets us reuse a lot of the existing logic. When we try to do an operation on a pool, we check against the list basically and decide if we should permit that operation. and that also determines whether the data sets are visible or not. So the namespace interface in Linux, the most common way to create a new namespace is to use the clone system call, which is a little like vfork, but has grown a huge set of flags to do all sorts of things to a new process, including spawn a new namespace for it. So we start with an empty list for the global zone, which currently, so for the first pass, we just have a list that has to be populated strictly from the global zone or the initial namespace. So containers can't modify their own lists of delegated data sets. But this already has an advantage of being able to modify that list on the fly, whereas in the zones implementation, it'd be baked into the initial. It would have to be configured before the process are started in the zone. So the other part is we're still limited to a mapping of one-to-one data set to namespace here. And we have to actually check if any of their children are delegated and not allow that. So the first pass looks like this. So we do ZFS list on the, so the first chunk of text is we're doing the ZFS list on the initial namespace, aka the global zone. So you see just a list of data sets in one pool. And this /proc entry refers to basically it's just a way to well it's actually lets you do namespace related operations so that you can open that file and do IOCTOs on it and so on. And so we've extended to basically so in the second block of text there's we've already created a new process running under new namespace, which I'll just call running inside a container. As you can see, it has a different dataset namespace, and currently the list of datasets is empty, and so ZFS list will return nothing. But if I modify that by writing to that kind of knob there, I can make a dataset available, and and you'll notice that it actually lists two datasets because the way delegation works is if you delegate a child dataset, it will be writable, but the parent will also be visible read-only. And now I can actually create datasets inside this container while still restricting the list of visible datasets. So the second pass, we try to make this a little bit smarter and try to get nesting to work. So start with the list being empty as usual, but now the list can be inherited properly by any new data sets we create. So if we create or by any new namespace that we create. So if we create a new namespace under an existing one, it'll inherit the same list of available data sets, and then we'll let everyone manage their own list of data sets, but they can only remove entries after the initial population. And this is to as a mechanism to allow kind of filtering down, but not you just can't add entries. And this also allows like the initial pass after we create a copy of the initial namespace to still have access to everything, because the empty list is interpreted as just don't filter. Anyway, so now inheritance kind of works, and then we can still kind of cull entries from that list as we needed. So in this case, okay. All right. So in this case, we do ZFS list in the host. And in this case, we can remove, we can list, we can add rather, the list on the host and container initially are the same full list, and then we can now then limit the list by writing to it once, and now it's filtered. And then notice that's done actually inside the containers. The container can remove entries, but it can never add them. And then finally, we remove all data sets available from the container. And then there's still a couple of issues. So dev.zfs is kind of problematic right now. If you make your world writable, users, it doesn't really do proper capability, or in the case of Linux, or privilege checking. And there's some user delegation that's also not really supported right now, because the user namespace support is necessary to kind of get all that all that together, so we can actually have secure containers. So also the surface area of the patching, although it's not too large right now, it probably could be reduced. They're like including like the way the user space interface works. So that's something I'm still considering. And then finally, we're also working on stuff with the new stable API that Richard Yao has proposed to make it easier for Go applications specifically, which is our user space, to work with that inside containers. And there's some other ZFS on links enhancements that we're considering. So, all right, thank you.